I'm not going to show this, the so-called Vetterick equation, I probably mispronouncing, which is this one. Okay. Okay. So, the thing about the renormalization group in lattice models is essentially that we are considering the Hamiltonian summon on each side. We will see that this will allow us to get the form of the potential for specific cases and find the critical energy due to it. One example that we can apply this is the Eisen model. So, how much time do we have left?
Very little. Well, not very little, but 10 minutes.
Oh, okay, let's say. Okay. So, can you see this? Yeah, I'll change it. So, for the Eisen model, we have the following Hamiltonian, which those are neighboring, right? Those are the spins. And we have an extra term solving, right? We can rewrite this R, U, R, prime, in which A is matrix. And from the Eisen model, we know that the eigenvalues of this matrix is just 2 beta J sum over V, 1D, given the number of dimensions that I'm considering, cosine of QV plus E. Alright, those are the eigenvalues of this matrix. To write the partition function, we use a trick which is called the Hubbard-Statonovich, I'm probably mispronouncing, which is to write the partition function. We can write it like this. Or F sum R prime R minus 1. Yes, the matrix is inverted, that's part of the trick. Natural log of hyperbolic cosine of phi. Okay? And from this, we can extract by analogy to the way I have previously written the Hamiltonian, the partition function. We get a Hamiltonian that is of the following form. Okay, it's the Hamiltonian you get from this way of writing the partition function, and by analogy to the original way of writing Hamiltonian, we can get the form of epsilon, so greater, and most importantly the form of the energy U, which
Try to avoid erasing formulas, because otherwise, because we are holding our questions to the end, but then...
sorry. I'll probably write smaller. I'm afraid my handwriting will be harder to read, but... Okay. That's the form of the potential, which I didn't mention, but that's the form of the potential.
I think most people are lost at this point.
Yes. So let me how much time do I have left? I'm going too fast. I'm sorry.
Yeah, you are at 8 minutes, so you still have 7 minutes, but you already lost everyone.
Okay. Let me.
It's my feeling. I might be wrong. Yeah.
No. Okay.
If someone is following, you can raise your hand.
Okay. Okay. Perhaps I do a brief recap of what I did. So we consider this Hamiltonian, which is sum over lattice sites, and the renormalization group procedure. We add this to the Hamiltonian, which the form of this RK is just this expression. Okay. And with this we can write the partition function this way, considering this external field. And from this partition function we get this expression here, which is the effective action, or in statistical physics terminology, the Gibbs free energy. Now I'm considering applying this to the Ising model, which is this Hamiltonian. And I can write this Hamiltonian by applying this matrix here. And this matrix has these eigenvalues, okay? And the partition function can be written in this form from this Hamiltonian. And the reason for why there is a -1 here is essentially because of the trick called Hubbard-Stratonovich transformation, which allows me to write it this way. Okay. From this one, for similarity with this expression, we get the following form of the Hamiltonian. Okay. And by analogy with this expression I wrote here, this is of the same form, we get the following form of the potential. Okay, that's essentially what I have done now. I'm not, of course, I'm not showing this steps. So we apply now the partition function with initial momentum k, which is a product of a partition function applied to each side of the lattice, okay, which are the form of the partition function on each side is essentially the same one here, but considering just each individual HR. And this I will not show this, but we can show that the potential that we wrote is initial squared divided by 2. And I erased it, but from the Vetterick equation, which I used before, we can find the derivative of uk with respect to k, which is just integral to k, or k is the normalization group. In which I introduce this row, which is just phi r squared divided by 2. Phi r is just the mean value of the field. Okay. Okay. So with this. got the. Yeah, just give me a second. Okay. Now, if we are considering a particle spin, we can get. I will not show this, but. Oh, sorry, I actually totally not created them.
Yeah.
I apologize. There's no more room there, but anyway. We can get a following form. Let's see the partition function. That's which someone is here. And plus the sum which are. As you can see, we can take this out, and this becomes just the product of the partition function on each side, which I wrote before. And anyway, I'll just go fast here. You can write on each side the sum of the spins, right? You have this one minus, this becomes 2 hyperbolic cosine of h. And by applying here, I will not show the math, but we get the form of the potential being O minus natural log of n minus 2O where tangents hyperbolic 2O minus 0 whole. And we can see when we do the derivative, we get something like minus natural log of 1 minus 2O, which just diverges as half, but the divergence locates this divergence that we got here. And with this we can numerically calculate the critical temperature by calculating the divergence of the susceptibility, which is essentially when this goes to 0. So we can calculate the critical temperature of the system. That's essentially it. So.
Okay, that's thank you. How many pages do you have?
On the paper or that I wrote down?
That you wrote.
That I wrote down? Well, I wrote quite some, but
Why?
from this
Yeah, I will give more comments later, but whenever you prepare a presentation, what you use to prepare is great, you can prepare notes, but the notes to prepare the paper and the notes for the presentation is something else.
Yeah, well,
Prepare all these papers, immediately people get the sense it's going to be a disaster. Because you have too much things and you are going to be selecting on the spot. That's a bad idea.
If I may say something about this, I first read the paper, and then after I made some notes, and then I made I think 2 or 3 notes about the things here. But I said, oh, I'll just show the math, I'll not. I'm sorry, I'll just show the formulas, I'll not, go shoot them very much. But perhaps it was a bit too much.
Yeah, just much. But okay, I'll give more comments about the presentation. Now let me ask about the physics. What is this paper about?
Oh, this is about applying a non-perturbative normalization group approach to lattice model. The main idea is that we start the Hamiltonian sum on lattices, and we apply the normalization group, which is that x of delta h, the expression we wrote, and we apply
So let me understand that step, because I think there is a misconception there. So what do you mean I apply the normalization group and therefore I start adding terms to them?
Well,
that's not how it works.
Yeah, because essentially we said that normalization is this right there, the transformation for normalization group. Right? We apply this to the Hamiltonian by restricting the number of degrees of freedom. That's the approach for it.
Okay, now you are starting to shift your words towards something more reasonable. So
yes.
You start with an Hamiltonian.
Yes.
That's the Hamiltonian.
Yes.
We are not going to, I don't think we are going to say that I touched that Hamiltonian. That's my UV Hamiltonian, is it not?
No, Huh?
Is it not true that I start with an Hamiltonian that defines my UV theory?
Yes, yes, but the randomization, yeah, that's right, that's Hamiltonian, and some over lattice side, so that's why lattice model. And the randomization group is essentially this, right? Change the Hamiltonian by restricting the number of degrees of freedom. That's the procedure of randomization group. What I did when I wrote that expression, Q R phi Q, that's the action of the randomization group, which I'm summing to this. I'm adding this Hamiltonian here. That's the procedure for randomization group.
Why is that the procedure? What's the connection between that and what we described last time, or the usual way we do things? Normally we do not add stuff.
Well, in this case, the randomization group is acting on the Hamiltonian by adding this expression of this.
Who ordered that stuff that you are adding? Why do you add that and not something else?
Well, that's the randomization group procedure, which again is 0, 5, 0.
Why?
I am unaffecting, I'm not changing this for high initial values, but for low, as you can see, when 0 smaller than pk, we sum over it, and essentially the Hamiltonian changes from E0 to ek. That's the procedure.
Let me try to see. So normally we have an Hamiltonian and we integrate things out. Namely, we say, for example, if I decompose in modes, I say I will treat the high frequency modes, I will integrate them out analytically. So I will separate, for example, the first term where I have a sum over mode below and above some cutoff. And then I integrate out explicitly the high cutoff ones, a thin slice, and by integrating out the thin slice, I derive some transformation law for the effective degrees of freedom after I integrate them out. So that's the usual way we phrase it.
Yeah,
we don't say, I start with an Hamiltonian, and then I start applying things and adding things to it. That's not the way I'm used to thinking. So
yeah, that's the way the paper shows to apply the randomization group. Essentially, yeah, for low frequencies, we consider this when the absolute 0 is higher than EQ, so this is unaffected. But when we are considering for low potential, then we apply this, and that's essentially how the randomization group enters it.
now, when we learn the normalization, we learn it in lattice and in the continuum, right? In the continuum, it's closer to what I described, and in the lattice, we all learn what is grouping spins into blocks, right?
Yes.
And joining Kadanoff and so on, and doing this lattice stuff. And we have all done some normalization example. So what you did was you went to the blackboard and you did a normalization example. But you did not tell us why is this paper important? Why do I care about this example? I mean, there are 1,000 examples of RG that we could discuss. And what is this paper about? Why should I care about this paper? Why is this an important paper? What are we doing? Why should we care?
Well, there are some advantages. For instance, I did not show this, but it enables to study classical spins model without deriving a field theory. This in the paper, I didn't show this. No, that's one of the. It allows to study everything like that scheme is preferable whenever the approximated flow equation gives a poor description of gamma. I don't know what's the Greek name of this letter? I don't remember. Gamma. Yeah. The non-perturbative randomization group lattice scheme is preferable whenever the approximated flow equation gives a poor description of gamma starting from the new field's results. I did not show this, but there are some advantages. I just do a simple.
Why did you choose to present what you presented?
I'm sorry?
What was your logic for presenting what you presented? Why do you think what you presented is interesting?
Well, I introduced the procedure for the randomization group, and I applied to a simple case, which is the IV model with this one. And with this procedure, we can calculate the shape of the energy, which is this one. And that's what I.
This applies to the IV model in 2 dimensions?
Yes.
In 3 dimensions?
Yes.
And what do you derive for those 2
Oh.
and 3-dimensional models?
Yeah, you can derive, for instance, the critical temperature of the.
The critical temperature is not interesting because it's lattice dependent, right?
Yeah.
So what else can you derive? Can you estimate critical exponents, for example?
Yeah, I think so. I mean, it doesn't show here.
Is it an interesting method for estimating critical exponents?
I think so. I mean, I don't think the paper shows this, at least not as far as I read, but yeah, I think so. I took this example. It shows other examples for classical spin models, but I took this particular example because that's what I thought I could present in 15 minutes.
What is the equation for this derivative? This derivative, there was an equation that you erased when I
Oh yeah, that is due to the because that's can be rewritten as 1 over n 5k of 5. I didn't put the 5 here. And there is the vectoric equation, which the paper does not deduce; it just shows, which is this one. Just 1 second.
Yeah. What's the physics and of this equation? Why did you choose to write to tell us about this equation?
This equation is needed to this equation. This equation needed to this. So this becomes
Derivative with respect to k.
yes, most k.
What is k?
K is this.
There was no k in the original anatomy.
Just give me a second. Sorry, it's the UK, which is the I would rename the
K is the cutoff?
yes. Yeah. Yeah, we did both.
Okay. Now then I understand. Any other questions?
Why does studying the current organization flow of this theory would tell us about theoretical exponents and etc.?
Well, essentially because we could calculate the shape of the potential here, and we can calculate others. Exponents, such as, for instance, this, as I said, I already put the susceptibility, for instance, can be given such as this, or 0, or equivalent the correlation with this. So when we calculate this, we can find the critical temperature, which in this case is 0.047 mF, which this mF is the result you get from applying mean field theory.
I think I was asking more what's the connection between RG and critical exponents and critical phenomena. What's the relation between?
Well, normally when we're studying the renormalization group, the way to find the critical exponents is essentially we take the Hamiltonian, we take the parameters that depend on the Hamiltonian, right? And we perturbate around the critical value, right? So, for instance, when we have this, we have the parameters that depend on the Hamiltonian, and we perturbate around the critical values, and the renormalization group around the critical values can work like this, right? So the perturbation group around this critical value is linear, and then there's the matrix, and you can find the eigenvalues of the matrix, and depending on the eigenvalues of this matrix, there are something like this, right? In which those are the critical exponents, and then you can find out by finding if the eigenvalue is higher than 1 or smaller than 1, so that's the relation. But that's a more general thing, I don't know if that's what you asked for. Yes. So essentially this is it for the procedure here. That's it.
Okay, let's thank you. And switch to a different topic. Are you going to slides or blackboard?
Yeah, slides.
Slides, okay. Do you have the slides with you?
Yeah, I have on email.
So what's your plan?
I can send.
Okay, do it then.
What is
the
it?
bathroom?
I can look in my email.
Do you want me to
You
read this?
can read to there like what's
Okay, I'll put
email if you open
Yeah, I can
email there.
log into my email.
Oh, but you lose points already. You arrived late and you did not think about how to plan the presentation in your phone.
It's because the
You don't have any USB pen or anything?
the secretary came to me to solve some bureaucratic stuff just before the presentation.
So what do we do? The computer is off. Why? It's not off.
Oh, there it is.
Esquenta na tela aí. Ligar o negócio. E depois você
Se você aperta,
tem algum e-mail para eu enviar a apresentação?
tá no meu. Eu
Ah,
posso.
você pode abrir o seu e-mail, tá? Também pode fazer isso.
Que merda é essa?
probably still about lattices, but now in a neural network setup, we will have Sydney. Very good. Go on.
So, I will try to present this paper, which is called Poissonian Renormalization of Neural Network Gaussian Processes. The authors are Jessica Howard, Ho Jefferson, Anijit MIT, and Zohar Bringel. This is a paper from 2025. It has 11 citations. So it's a quite new paper. And let's get started then. So first, I'll introduce our problem, which is to deal with neural networks. And then we will try to understand neural networks from a perspective of physics, where we will look for networks in the large size approximation, so we can use techniques from statistical mechanics and field theory. And then I'll present what the paper has presented as the results comparing, applying the theory that they developed. So, neural networks are mathematical abstractions to describe some data. So, they are an algorithm to learn patterns from the data and different kinds of situations. And you can do lots of stuff like learning signals and image recognition, also correlations in text and various data. And how it works. It is built on the idea of neurons, so it has some perspective on, it is motivated by the functioning of the brain. So it has neurons take some inputs, their signals, and they perform an operation on the signals, and they project an output, a result, based on the signals. So they take these signals and multiply them by some matrix, add a constant term called bias term, and then it goes through a nonlinear activation function that you may choose depending on your application. And the network is a combination of layers of different neurons. So each neuron will receive some inputs and will speak some output, which will be the input for another neuron. And you combine these neurons and you create a network of neurons, which at the end will provide an output, hopefully a good output, a prediction for some data. So
we can see the...
Okay, here's the equation for nth layer, and you can see that this is a recursive equation that will take the results from the n-1 layer, and we will obtain the nth layer. How they learn? First, we take some data that we are trying to model, and the network will make a guess. Based on this guess, we can calculate a loss function, which will measure how our prediction from the network deviates from the true result. An unusual choice for this loss is the mean squared error loss, which is also common for regression problems. You can have another losses also, like logistic loss and so on. And after we calculate this loss, we can update the parameters on the network, mainly the biases and the weights, by computing the gradient of the loss with respect to that parameter, and then we can move in the direction that we decrease the loss. So we do that many steps until we say, well, the network produces a loss that is not so not big, and it does well in our problem that we are interested. So we can take this and look for an approximation of the network, like taking a tangent plane to a manifold, and we look for a linear approximation of what the network is doing. This is called the NTK short for neurotangent kernel. And we can see that the variation of the loss after we do one step on our parameters is given by a scalar product of the derivatives of the losses with respect to the neurons with this operator which is called the neurotangent kernel. So the variation of any observable of the network is given by an expression like this where there appears this operator which acts linearly on the thing we are going to change. So some applications of neural networks are speech and image recognition. We can also generate text and image, as you may already know with ChatGPT. We can automate some tasks. The algorithm will be somewhat different because there's no loss function automation, but that's another talk. We can also solve differential equations if we set the loss to be the difference of the prediction of the neural network and what is the result of a given equation. We can test this without needing to solve the equation exactly. And there are many more other uses for neural networks. So, there's a huge success in neural networks for various kinds of tasks. But their intuition and how they behave is still somewhat missing, is incomplete. So, common machine learning theory does not predict this very good success, and we need other techniques to understand what is going on in these systems. So, as physicists, we use physics to understand this problem. And one of the problems we are very interested is called AI sleeping walls. So we take various networks and compare how well they behave. So if we take, for example, the test loss and compare it with the time it's taken to train the network, it behaves like a power law. And there are other power laws here with the size of the training data and the number of the parameters in the network, all making the loss decreases. And there are many more scaling laws. All of them are in the paper, which is out of this. Okay, so this paper is by Kaplan at 2020. So we can work as a physicist. We can view the network as a field. If we take very large networks and approximate the number of neurons to infinity. In this region, we can use techniques from statistical mechanics and field theory, and then we can hopefully describe something else in the network. So, in this limit, the neurotangent kernel does not vary very much. It is almost constant, and with that, we can approximate the network as a Gaussian process because you have infinite neurons, then central limit theorem will work precisely in this limit. And then the network becomes a Gaussian process with a Gaussian kernel, and our predictions, given some data, will follow this equation here, where this kernel, K is the neurotangent kernel, which is frozen and constant, will not vary. And given this expression, we can create like a lot of copies of the network and see how they behave collectively. This is called the replica tree. And for it, we can calculate a partition function based on this equation. So, if we train with eta samples in the training data, our partition function becomes this one, where we write an effective action as this expression right here. I will not derive this. This is a very long calculation, and if you are interested, you can ask. Oh, so you can see that there is a Gaussian term here connected by the inverse of the kernel, and there's a difference from the Gaussian process description of the data and the true data square. So this term will try to minimize this difference, while this will take some part of the noise contained in the data that will appear here. So we can expand everything in our problem, the function itself and the data in terms of eigenfunctions of this kernel, given by this equation here. It's an eigenvector equation. And if we expand it to modes, the action becomes simpler. It's a sum over all modes. So, with this action, we can compute the mean and the variance of the predictions. So, we have a term that grows with the value of this eigenvalue of each mode, but there is also a noise term, and the noise term is expressed by how many data you have. So the more data, the less the noise is important, and the more you can approach the eigenvalue. So ideally, you would have only this, but you have not. Oh, sorry, ideally you would have like the mean predicted is equal to the true data. And also the variance, so there's noise, the prediction is not perfect. How much time do I have?
3 minutes.
Oh, okay. So, one thing that the paper did was, we have an action and we have some noise. There are modes with very high eigenvalues, so these will be easier to learn. We will approach the true value of the data for that mode. But there are modes for which the noise becomes very high, so these modes are practically unlearnable. So we can use an effective theory if we integrate out these modes that have eigenvalues much less than the noise that we have in the problem. So for that, we can construct an effective partition function based on a cutoff given by this term here, which is proportional to the noise. With this, we can write an action based on the partition function, and this action will have a term that is due only to the high eigenvalue modes, and some interaction of the high eigenvalue modes and the low eigenvalues that are not learnable. This interaction is also Gaussian because we are in the infinite limit of the network. It has this expression, and we can see that in this Gaussian we have a coupling which is proportional to the noise of the data and a correlation matrix between the different replicas that we have of the different neural networks. So, based on this action, a procedure that we can do is that we can integrate nearest the cutoff, we integrate the modes that have eigenvalues slightly below the cutoff and the cutoff. And if we integrate that, this coupling constant will change, much like in the renormalization group flow. So, we can write this, we can do this procedure and compute the new coupling constants. And if we do recursively that, we will arrive at a theory that only contains the learnable modes from the data. So, based on these steps, the authors, they calculate this for 2 real data sets. And they can compute all these steps numerically and proceed with an approximation of, they have an effective theory of the neurotangent kernel. And here are the results. So first of all, these dashed lines are the neurotangent kernel approximations. If we do not do these effective theories, we can see that they overestimate the capacity of the network. They predict a very small loss. But if we work in the effective theory that they presented, we have these solid lines, which almost perfectly match the data. So they also compare with the state-of-the-art model for approximation, which is called the spectral bias. I don't know much about it, so don't ask me. And they compare it for the NS dataset, which is a dataset of handwritten numbers where you predict the number which is written on the image. And they compare it on the CIFR10 data, which is some images of a lot of different stuff. And you try to predict what is on the image. So that's it. The paper goes much deeper than that, but that's what I can present. And thanks for.
Very good, thank you. We went just a little bit over time. Questions? All right.
Yes, so essentially this allows for training models for AI.
Yeah, not training, but explaining what you can learn from the data and what you cannot learn given the noise.
One thing that perhaps we can go back, when you express neurons, for instance, what are exactly neurons there? Are they like mathematical function? Or
Yeah, they are an abstraction. You can write a function for them. Like, they will have a value which is given in terms of a function of what was given for.
so each AN is like a neuron?
Each and here is a layer, and the neuron is, there's an index here. This is the neural index of each layer.
Oh, okay. So it's like it's a graph.
Yeah, it's a graph.
Okay, yeah. Oh,
You can say like things over Gaussian, because they needed should be Gaussian, but this is not true, right? Like Gaussian here, it's approximation. You are throwing away some like effects. Could you use the same for doing things with a non-Gaussian action of this neuron?
I'm very happy that you asked that. That is the next step of the paper. Like, in the infinite limit, everything will be Gaussian. But real data is not Gaussian, and we want to capture the non-Gaussianities of the data. So, for example, in the large network limit, we can do a perturbative expansion on the action, and we can add a term like 1 over n, where n is the number of neurons, times a quartic coupling, which will be the deviation from a Gaussian. We can also perform this, which will be way harder, of course. The paper did it, but I didn't have time to work with that. But it is possible. You can add terms in this action, and it will be just more complicated.
I think I have exactly the same question as Gabriel. Why is it Gaussian?
Because we are taking in the approximation of infinite networks.
I mean, that's I think the step that is a bit too fast for me. I don't follow that logic.
Oh.
Can you say a few more words?
Of course. want a very large network to learn a lot of data.
Yes.
But if you work with finite networks and try to do analytic stuff,
Don't forget about finite networks. We have a very large network, so it's like a very large lattice.
yeah,
Okay?
you
You're
are.
happy with that? Why is that Gaussian?
Oh, it is Gaussian because each neuron here will be a combination of infinite other neurons with infinite number of parameters here summed together. So if you ignore the activation function for a moment, this term will have a Gaussian distribution, right?
Maybe that's obvious, but can you just remind us? So, let's see, our confusion, I think that, or maybe my confusion, but is that when we have a lattice, not all lattice models flow to Gaussian continuum theories. Some do, some don't.
Okay.
Why does this one flow to a Gaussian theory versus, for example, the Ising model, which was also an infinite lattice at the previous talk, and Pedro was not saying the theory is Gaussian, and we can solve it, but you are saying the theory is Gaussian.
Oh, okay. So at initialization, you start with all parameters randomly chosen by some Gaussian distribution. It can be other distribution, but the usual choice is Gaussian.
Okay,
And you sum a lot of Gaussians, and this will produce a Gaussian in the next layer, and so on and so on. In the learning, you would expect that the distribution will change. But in the infinite limits, the neural tangent kernel doesn't change. So it changes infinitesimally.
Like so infinite, like infinite number
Of neurons in each layer.
Of layer? Okay, of neurons in each layer.
It can be finite layers. If it's infinite layers, then it will take infinite time to compute.
I think our confusion physically is, it looks like you are saying that if you add infinitely many layers, things become easy.
No, infinite
That's
many
what is
neurons.
confusing us because things are supposed to be complicated. They are not supposed to be trivial. These models do very complicated things, as you explained. So, I think in our mind we are a bit confused because how could something do something complicated and be Gaussian? At least that's my confusion.
Okay, so
But I think it's related to learning versus not learning. So,
yeah, like when you are in this infinite learning, infinite approximation.
is it not true? Infinite approximation is like having lots of computers. Like Google is almost infinite, right? They use lots of layers, lots of nodes, and so on.
Yeah,
So in practice, they are in the infinite limit, and of course, we cannot do anything analytically. So I'm confused with this notion.
no, you can do analytically, but this will introduce interactions which will come like interactions in the action. You can do perturbative stuff. The Gaussian approximation is not a good approximation for the data, but it can explain the learning of these modes where the eigenvalues are larger than the deviations on the Gaussian process.
Okay, so now in your answer, you said something that contradicts what you said before. Before you were saying it's infinite and therefore it's Gaussian, clearly. And now you are saying Gaussian is a bad approximation. Which one is correct? Is Gaussian a logical consequence of something being infinite or no?
Oh, the truth is that true infinite networks are not good networks.
Okay, why not?
Because infinite networks can only capture Gaussian correlations between the data. They cannot take into account interactions like higher order correlators.
That sounds impossible to be true. I can have an infinite lattice and not activate many neurons, and that's a finite lattice.
Oh, that is
Having an infinite lattice cannot be bad.
it can be. In this case, it won't be very good. But due to the finite effects, you can learn more. That is totally counterintuitive, I know.
At some point you said that maybe it's stupid question. At some point you said that these interaction terms they have 1/n number of sites. Why is that?
What is that?
Why?
Why? It's the next term. If you do like perturbation theory, the cubic term is 0 due to the symmetries of the network. And the next term that you can compute the corrections is the 4th term. And it will appear as a 1/n coupling factor. If you open the calculations, it will appear clearly, believe me.
So can you repeat once more? You are saying that we have an infinite amount of layers, and perhaps
Neurons in each layer.
neurons in each layer, but the number of layers is finite.
Yeah.
Is that important, by the way?
Yeah, if the number of layers is infinite, there will take infinite time to compute.
Okay, so we have a finite number of layers and infinite number of neurons.
Yeah, you can also work in the limits of the two going to infinity.
And the key thing is that it's all to all, right? So it's one neuron knows about all the neurons of the previous layer, so it's a very non-local thing.
Yeah.
And it's that makes it Gaussian, right?
Yeah.
But what is wrong in our intuition that these models need to do complicated things and Gaussian models do trivial things? Still, I'm missing that basic.
I have a related question, like what's the regime in which the Gaussian is a good approximation? Like what are the assumptions that make the Gaussian a good approximation? And so when do like it's not enough, like when is Gaussian like not enough?
So when you start training a neural network, the first thing you capture of the data is the Gaussian correlations, like the 2-point correlators. But after you train, this won't be a good model. You need like terms in the interaction that captures like 4 correlators that separates from the two correlators. Like there are interactions that do not factorize as Gaussian interactions. So you can compute like Feynman diagrams for this kind of stuff.
So I assume in some like regimes this will be important. This like fourth-way stuff, but in some like other regimes it to not be important. Like in which they will be important, and in which they will not be important. Like what are the assumptions that make them important or not?
Oh, it depends heavily on the data. What are you trying to learn? If you are trying to learn simple correlations in your data, this is perfect, like 2-point correlators. The specific regime is a very complicated question because you need to predict what is going on. So you need to go on for the next terms in the interaction and see what is different. So I did not do that. The paper does it. And yeah, I would very like to explain that, but it's still, it is a complicated problem, I promise.
Good. More questions? Let's thank Sydney. Okay, let me make a few comments about the presentations. So, Pedro, I already said some of the comments that I had. I think my impression was that you prepared the paper, but you did not prepare the presentation. You You were taking notes to prepare the paper, studying the paper, taking your own notes, and then once you were done, you thought, okay, now in the presentation I'll present a subset of this. And that you cannot do because it doesn't work. You need to do two exercises: prepare the paper and prepare the presentation. It's a separate thing. If you try to do both, you will struggle with deciding on the spot what to present. Yeah. Don't erase stuff when you give a presentation in the blackboard where the questions will be at the end. Otherwise, it will be a mess at the end because people will want to ask questions. No, you should have used only that, because if you only have 15 minutes, you should definitely have chosen material that will only occupy that. If you have to erase, it's a bad sign. You are doing too much for 15 minutes. In 15 minutes, you should not. You did apologize for your handwriting, but you do have to work on your handwriting, because yeah, you need to improve it. It can be improved. You just need to practice more, or write more calmly, and pick. It's related to the previous thing, because you did not select so much what to present and what not to present. You were writing too much, and therefore, of course, the handwriting was not coming across okay. So, yeah. So for the presentation, I would say it should be better. I could give you a 6 or 7. I think it was. You forgot important things. Explain why we are doing this paper, right? It was a bit, you just started doing some computation, so so for the presentation, I think for the physics it will be the same thing, that I think the physics of why this paper I think was important, so was missing. I think in the questions it was a bit better. I think when I asked you to summarize, you were summarizing okay. You have again to commit to being pedagogical or sharp. You almost did it, for example. You wrote this icing and then you said it's possible to go to this presentation. But it was a bit unclear. I think you have to stress that you are not explaining, that you are stating. And you kind of did it, you almost did it, but you have to emphasize that. Otherwise, you start explaining because you are explaining things. I have this, I write this delta k, and it's like an explanation, and then it's not an explanation. This is a chunk. This is a statement. If this Hamiltonian is equal to this, there is a transformation. And indeed, I mean, after you explain it's obvious. You just you resolve that S square, introducing some extra field, right? So you complete the square, that's what they call a rounded. But you have to state it, you have to say statement. This is equal to this, I mean, it's a true statement, right? Then it's fine, you don't need to explain. But you have to really commit to being sharp or being pedagogical. Don't try to do both. If you try to kind of explain but not completely, it becomes a mess. So you have to decide, this point I will explain. Fine, explain. For example, you write an equation for a derivative and so on. Do you need that equation? So either you say sharply what this equation is or explain it. But don't do something in between, saying, then they compute this derivative because it's important in this computation and we don't understand. Should we try to understand? Or is this just a statement that this equation is important? So always commit to being pedagogical or being sharp. And be careful. You can alternate, but be careful with us. So, yeah. But I think the main thing that I think will improve your presentation a lot is prepare 1 page, at most 1.5 pages only for the presentation, and preparing the page to present on the page for you. It's good that you take notes and prepare, but it's not the same thing. Let me ask you one thing. What do you work on, and what's your level? Are you a master, PhD?
Master. Second year of my thesis is about geometry of ADS deformations. I'm under Andre.
ADS deformation. Just curious. Okay. And Sydney, you work on this field probably, right? Because the beginning, I thought you learned it so quickly. This beginning part, it's something related to what you work on, right?
Yeah.
Okay, that makes sense. So, who do you work on and what's your level? A master, PhD?
PhD, I work with Roberto Cranky.
Okay. So, I thought overall your presentation, physics, and question was very good. I mean, I would say probably 9 on everything, but I do have some comments that I think you can improve. So, I think you more or less went on the right level. which made it a bit rushed in the paper itself. So physics comes to the rescue and so on. We don't need that. I mean, you need to be a bit more to the point in the beginning. Again, thinking what's the target audience? Is it people that do not know about neurons at all and you really want to explain what a neuron is? Fine, you can explain, it's easy. But you probably were assuming that we all heard already some colloquium about this, which is fine. I mean, nowadays everyone knows what a neuron is and so on. Then so you have to think a bit who's the target audience when you give these introductions, because sometimes it was not clear if you were trying to. You cannot assume that everything you said was new, and then we would understand this, because that's impossible. We cannot learn all the knowledge. If we knew nothing, we could not get to this point. If we already knew a bit, fine, you can refresh a little bit, but you have to commit to who is the target audience when you are giving a slide at all. In the beginning, and then when you were answering Pedro, you used the word abstractions. Very bad choice of words. It makes people nervous. What are you saying? An abstraction. It's an abstraction. It's a function. These neurons, when you said neurons are a mathematical abstraction, it looks like dark magic. But what's a mathematical abstraction?
Well, I should have said a mathematical abstraction.
A function. But what exactly do you mean? I don't know that. Mathematical abstraction. It's just you are not using
precise. It's just a model.
But the neuron itself, a neuron, I felt, and I think Pedro in his question, my impression that he felt as well, that it was probably something that you could just explain sharply what it is, and instead you were giving it an hour of mystery for no particular reason. In these models, everything is very clear, right? There is this activation function, there is the neuron, there is this and that. It's nothing mysterious. It's not like an abstraction of reality to code, blah, blah. I mean, it's something concrete, right? A neuron, you could say it's just this function that goes from one layer that updates the value at this point, knowing the previous point, or something like that, right? So just be careful when you are doing sharp statements, but then the sentence becomes not sharp if you have some word like abstraction or kind of, or you immediately destroy the beauty. You had a beautiful sentence with this abstraction in the middle that it's a bit ambiguous what exactly that means. Then you have this MTK slide, which has several steps, and again it was not clear why those steps, because in the end you only cared about the final. Were you going to explain those steps, or why was that equation with lots of equal signs there when you did this MTK? So it was a bit unclear, should I be trying to follow the steps, or should I just look at the final result? It was again this thing that you have to commit. Either you are pedagogical or you are sharp, and that slide was a bit funny. I was not clear why those equations were there, but it's not a big deal. It was just, for me, I did not understand why the MTK equations were there. But that's fine. That's maybe not a serious comment. That's not important. But otherwise, I thought the presentation was good. I thought you motivated well why the paper is relevant, how it connects with the course, and so on. You needed a bit more time for the paper, a bit less time for the introduction, that I said already. On the questions, I think you answered well. I think you did something well, which was when I said, I'm still not sure if I buy it, but when I said if the lattice is infinitely big, the results cannot become worse, I think you said something very good, which is you said, I know it's counterintuitive, but it's true. This is extremely good. This is a very good answer, because it really helps me take the point across. If you are confident, that's a good answer. You say, yes, it looks counterintuitive, I increase, and it should become always better, but no, it becomes worse. If you could say, the reason is that I'm overfitting, or the reason is, that would be even better. But it was already very good. It's a good thing to do. This asking and answering questions is like a dance. It's also, you should not just accept all the questions are good and so on, and you should say, no, it looks counterintuitive, but it's true, it becomes worse. I thought that was very good. Yeah, I did think that the explanation of Gaussian, that's why I did not give a perfect score. You are probably right, you must be right, but you saw that people were a bit confused about why is it obvious that things are Gaussian, and yeah, I think that you did not address very clearly why it's Gaussian. You said something about large numbers and so on, but I think either there is a very clean reason that you did not convey it, or it's just an approximation that is not justified, but it kind of works and you did not state it properly. So I think that Gaussian step was the weakest point in my view, and also the step when you start discussing replicas. Probably there are some words that were missing there. Suddenly we start discussing replicas and it was unclear why we start discussing replicas at that point.
Yeah, I should have
You
explained.
also either skip it or explain it, but that can be a bit confusing to people. Now when we have replicas, okay, I can kind of see that why replicas could appear, but you did not explain it, so you have to be careful with that. But it was a good presentation. So next presentation, give it in the blackboard. It's good practice to train both presentations. Maybe next presentation you could try to do slides. Because it often happens that I have had students, I don't know, my student Arish, for example, his slide presentations are much better than his blackboard presentation. And my student David is the other way around. His presentations on the blackboard are much better. So it depends. Some people, I think your presentations on slides are very good. You already have a very good starting point. You can still improve them, as I said. But let's see the blackboard. Often the blackboard needs improvement and vice versa. And for you, maybe it will help you not go over time and make sure that the slides have sharp statements and that you alternate between sharp and pedagogical looking at the slides. It might help you. We will see. So. Okay, so that's it. Thank you all. And so on Friday, I will talk about the parking paper. Thank you, Love. Same place there. Okay, very good. Can someone please take this upstairs and give it to Gary? Okay. Thank you. So maybe at 1:45. I am going to lose an email now. Okay?
Now, and then we have lunch, so 2 probably.
Okay. Very good.
Ciao, ciao.
This is very important to practice this presentation because you see that.
Yeah, I thought about doing slides, but as you said, I remember when we were correcting them, you said, oh, it's not a good idea to use slides to just write the equations.
No. Put more material, no. But sometimes for some people it's important to have the sharp statements there, not to forget to say them. Yeah, don't use it as an excuse to put more material.
I think I will try.